All right, class, we're going to be looking at exponential functions in Chapter 6, exponentials and logarithmic functions. An exponential function for any real number x is a function that can be written in this form, f of x, whoops, whoa, that was weird, f of x equals ab to the x power. So now we're looking at x being in the exponent versus it being a non-exponent, right? So if a is a non-zero real number called an initial value, and b is any positive real number such that b cannot equal 0. The domain of f is all real numbers, so we can plug in anything into the function abx. The range of f is all possible real numbers from a, as long as a is greater than 0. The range of f is all not all negative real numbers if a is less than 0. And then the y-intercept is going to be given to us as 0, a. And the horizontal asymptote here is y equals 0. Now, we can, from time to time, we can see the function looking as y is equal to a b to the x. So remember that a is our coefficient. X becomes our variable up here. And then b is what we call the base. And the base, and it can be any number. Right? And we're going to talk about b more in detail in a little bit in terms of if we're seeing a decay or a growth, and we'll get to that in just a second. Which of the following equations are exponential functions? So thinking about the fact that an exponential function is going to look like this, right? Go ahead and let's call this A, B, C, and D. And what I'd like you to do is go ahead and mark A, B, C, and D to which ones you consider exponential functions. All right, so hopefully you said that A was an exponential and that B is an exponential, and we can see that both of these are exponentials because our variable is in the exponent's location. Here, our variable is in the constant, and here this is actually looks like a linear function here, and here we have a degree 3 polynomial, cubic polynomial. So we have two exponential functions. All right, let's look at this problem here. We're going to talk about evaluating. So we're going to do, when it says evaluate f of 2, remember this just means we're going to plug in x equals 2. Okay, so f of 2 is just telling us plug in 2 for x. So let's come over here, and here's our function f of 2. So we're going to do 5 times 3. Now this is going to be raised to the 2 plus 1. So when we plug this in, we're really doing 3 to the third power. So we're going to evaluate the exponent first and then multiply by 5. And so if you put that into your handy dandy calculator, you should see that this will equal 135. So remember, all this means is we are saying what does a function equal when x equals 2. All right, let's go ahead and evaluate for f of equals to 3. Go ahead and try this on your own. All right, did you get f of 3 is equal to 5.5? In this case, notice that our exponent does become negative, right? So if you're using a calculator, make sure that you're using the caret and you're inputting both the negative and the exponent there. And so what that's going to do is it's going to turn this into a fraction. So it should be 8, and then now you're dividing by 1.2. Okay, and so we should get 5.5 as the solution there. All right, exponential growth. So now let's talk about exponential growth here. So a function that models exponential growth grows by a rate proportional to the amount present for any real number x and any positive real number a and b, such that b cannot equal 0. An exponential growth function has the form of f of x equals abx. Notice that it's the same exponential function, right? Now, this is where it becomes a growth. A is initial and starting value of the function, so we want to keep that in mind. B is the growth factor or growth multiplier per unit x. Okay, so let's take a look at this example. In 2006, 80 deer were introduced to a wildlife refuge. By 2012, the population had grown to 180 deer. The population was growing exponentially. Write an algebraic function, n of t, representing the population of deer over time t and the number of years since 2006. Okay. So let's go ahead, and I think it's really important that we define our variables. They're somewhat already defined in the problem, but let's go ahead and define them. So we are going to say t is going to be the number of years since 2006. N of t is going to be the population of deer. So we're going to set this up because we know it's an exponential function. This is going to tell us that we are going to have something that looks like n of t is going to equal a times b to the t power. All right, so this is what we want to find. Okay. Now, a, remember, a is our initial value. Okay. So we need to look at, when we look at back to the problem, right, what do we know? We know that we started off with 80 deer, and then it grew to 108 deer by 2012. So in 2006, we started off with 80 deer. And remember, t is the number of years since 2006. So that is our initial population there. So let's do a real quick chart. So here's my year and my population. Okay. So remember that year is t, and then my population is going to be that n of t. So in year 2006, which in this part, this is critical for us to consider that in 2006, this is really what we're calling 0. I don't know why my stylus is freaking out. And then we have 2012, and then, so if this is 0, so we can move this up. There you go. If this is 0, how many years from 2006 to 2012? Well, that's going to be 6 years, right? So if we started at 2006, how long till we get to 2012? That's 6 years. We know that the population in 2006 was 80, and the population in 2012 was 180. Okay, so now let's take a look at this. So we know our initial value is going to be at 0 and 80. So we're going to have our n of t is going to equal, remember, a is our initial value, so we're going to start off with 80, and then that's going to be times, we don't know what that growth rate is yet, right? And so this is to the t power. Okay. Now, we do know that the population was 180, right, when 6 years had passed. So now we're going to solve this. So what we're going to do is we're going to go ahead and divide by 80 on both sides. And so now this gives us 2.25. And now this is b to the 6th power. Okay. So how do we solve this? Well, the way that we do this is we're going to be using exponents. So what we're going to do is we're going to raise both sides to the 6th power. Or you can think of this as also taking the 6th root. So we're going to take the 6th root of both sides. Or this is the same thing as saying 2.25 raised to the 1/6 power. So when I raise it to that fraction power, remember this cancels out, these cancel out. So I'm left with the 6th root of 2.25, which gives me that this is 1.1447, 1, etc. And this equals b. So let's go ahead and round to 3 decimal places. So here's 1, 2, 3. This is going to tell this to go up, so we're going to have 1.1. Sorry for the noise. 1.1447 4, 5 equals b. So this tells me that this is my base. Okay. So now what we want to do is we want to write out our equation. So here's our n of t. We know that our initial value is 80. I now know that my base is 1.145, and now I'm going to raise that to the x power. And this is the equation we were looking for. Yeah. All right. All right, so now we're going to find an exponential function that passes through the points -2, 6, and 2, 1 by hand. Now, because we don't have the initial value, we're going to substitute both points into the equation of the form of our exponential function f of x equals ab to the x power. So then when we solve the system, we're going to solve it for a and b. So let's go ahead and do that. So we're going to have, let's plug, oh my goodness. Let's plug in the first one. So we're going to plug in 6 for our f of x, and then we're going to have a, b, and then we're going to have that to the -2 power. So that's our first function. Our next function is going to be, again, we're going to use the same form, except now we're going to plug in 1, and we're going to have a, b to the second power. So we're going to use the first equation, right, to solve for a in terms of b. So we're just going to kind of move this around to make sure that we have a equals something. So because this is a negative exponent, let's go ahead and rewrite this equation. So we're going to have 6 equals a, and notice that we do have the exponential rules that tells me that this is the same thing as saying a, b to the second power, right? And so now what I can do is I can multiply b squared on both sides. And so notice that my b squares cancel out, and I'm left with 6b squared equals a. And this is what a equals. So now I can take this and I can plug it in to this equation here. So now I would have 1 equals, and I'm going to replace a with 6b squared times b squared. So remember, this was my original a. So now let's go ahead and do the algebra here. So notice that we'll get 1 equals 6b squared times b squared. That's going to give me a b to the 4th. So let's go ahead and divide both sides by 6. And I end up with 1 over 6 equals b to the 4th. We're going to go ahead and get rid of that exponent. And so we're going to take both sides and we're going to take the 4th root of both sides. So when I do that, the 4th root disappears, and I'm left with b equals the 4th root of 1 over 6, sorry. And so this is approximately, b is approximate to 0.6389, okay? So now we know what b is, so we can go back and plug it in to this equation. So we're going to have 6 times 0.6389 squared equals a. So when we plug this into our calculators, we're going to get 2.4492 equals a. So we found both our a and our b, so we can now write out our equation to be f of x is equal to our a, our initial value, so here's 2.4, times that by our base, our b, so 0.6389, and that's going to be raised to the x power. And that's it. All right, go ahead. And now we're going to be looking at the same exact problem, now doing it on our calculator. All right, so in order to do this on our Desmos calculator, I'm going to go ahead and pull up the Desmos calculator. And so let me actually, I had the points already plotted, but let me show you how to do that. So we're going to go ahead and click on our cell here. This is just the Desmos graphing calculator that we have been using. I'm going to go ahead and press the plus button that says add item. And so notice I want to add a table. So it's automatically going to give me x1 and y1. So we're going to go ahead and plot the values that were given to us. And so we have -2, and -2 has a y value of 6. And then we have 2 with a y value of 1. So now I can go ahead and change these colors if I want, but that color is perfectly fine. So now what I'm going to do is I've plotted the points on one line. On the next line, what I need to do is I need to type in y, and we need to do a squiggle. So we're going to do shift tilde or shift squiggle. It's the key right next to the 1. And so we're going to get this little tilde, which means approximately. So then we're going to put in our function AB, and now we're going to do a caret, so shift 6, which will bring us up. You can also use this button right here, the AB button, and then we're going to write X, and then let's make sure we write 1. Oh, you know what? I forgot to write Y1. And so once I do that, this is telling Desmos to go ahead and approximate what we have there, what is based off of our variables at the top. So that's specifically why we need to use y1 and x1, because we're telling it to call the variables that are up here. So notice down here, our a and our b are given to us here in the parameters. Whoops. Here in the parameters, and so we see that A is 2.44949 and B is 0.638943, which is exactly what we had before. So let's take a look and rewrite that. See if I can make this narrower. So now we can see that our A is equal to 2.449, and our B is going to be equal to 0.6389. Okay, and then this is 49 out here. But we can go ahead and round this. Let's round this to 2.4495, 4 decimal places, and then we have 0.6389. Okay. All right, so let's just try this one more time. Sorry for the noise. So what we want to do is first we're going to come over here, and let me see if I can move this window. So we're going to come right back over here. We are going to add the plus button, and we're going to hit table. We're going to input our values. You know, let's put in different values now. So 2, 6, and maybe we have 3 and 15, let's say, right? And so now I'm going to come back over here. We're going to do y, our y value. Make sure we do shift tilde. And remember, the tilde is right next to the 1 on our keyboard. We have AB, and we're going to raise that. So you can actually push this button if you like. Oh, you know what? I forgot the 1. So it has to be y1, because we need to call the variable from before. And then this is going to be x1. And so there's our function. Notice here's our A, our initial value, and then our B, our growth. So that's how we would use the Desmos calculator for doing this type of problem. So just to finalize this, we'd end up with f of x, our initial value is 2.4495, and then our B value is 0.6389, and then this is going to be to the x power. Okay. We can reduce this. I'm actually thinking we should just do this to 3 decimal places. It's a lot of decimals. All right, so to the 3rd decimal place, that would go over. So this would end up just being 2.45, and then 0.639 to the x power. So either one of these is okay. Okay. All right. Now, I would like you to take an opportunity to try this one. All right, use your calculator or your Desmos calculator. And try this one out. All right, is this the function that you got? Hopefully it was. Let me know if you have any questions on how to do that. Okay. All right, let's take a look at compound interest formulas. So compound interest can be calculated using this formula here. AT is the account value. T is measured in years. P is the starting amount, often called the principal, right? So that's our initial amount. R is the annual percentage rate, the APR expressed as a decimal, and N is the number of compound periods in 1 year. Okay. So let's take a look at this example. If we invested $3,000, so this is going to be our principal. That's what we are investing. Paying 3% interest, right? So here is our interest. Okay, that's our rate. Compounded quarterly. So if it's compounded quarterly, this is telling us that that's going to be 4 times in 1 year. So this is going to be N equals 4. Because remember, the N is the number of compound periods in 1 year. So if it's quarterly, it's going to happen 4 times a year. How much will the account be worth in 10 years? So this is our T value. Okay, so let's go ahead and I always start this off by writing out all the variables. Even though I identified them in the statement here, let's do P is going to be equal to 3,000. We have our R, that's going to be 3%. So 3% as a decimal is going to be 0.03. We have our N is equal to 4, and then our T is equal to 10. So now we come back up here. Remember, we're just going to pull this formula here. So we have our A of T, which is what we are interested in, is equal to P times 1 plus R over N to the NT. So let's go ahead and plug in these values. So A of T, our principal is going to be that 3,000. 1 plus our rate, 0.03, over N, which is 4, to the N times 10. Okay, so our A of T. Then we're going to just plug this into our calculator. Be careful with the way that you plug in this part here. Take your time with this, right? But when we plug this all into our calculator, right, we will see that our value is going to be in dollars, so it's going to be 4,045 and 05 cents. Okay, so we can write this out in a sentence saying that the account will have $4,045.05 in 10 years. Okay. All right. So in this one, we're working a little bit backwards. And I'm going to give you a second because I want you to try it out at least. See if you can figure this out. So here is the total after 15 years. 4% interest rate compounded monthly. What's the principal? Okay, so see if you can at least set up the equation. So pause this, set up the equation, and then we'll continue. All right, so looking at this here, notice that we know what our A of T is, right? So I wrote everything out. We don't know what the principal is. That's what we are curious about. We know what the rate is. We know what N is, and we know what the time is in 15 years. So we should have something that looks like this. Okay. So let's go ahead and see how much of this we can solve. So we're basically finding the P value here, the principal value. So we have 192,000 equals P times 1 plus 0.04 divided by 12. All right, so this inside would equal 1.0033. This is going to go to the 180 power. Okay. So when we take that value, oops. So when we take 1.0033 and we're going to raise that to the 180th power, we end up with P times 1.809448. So now all that we have left to do is going to divide these amounts. So let's go ahead and divide both sides by 1.809448. So then, once the division occurs, this cancels out. So we're left with P equals 105,477.02. So just to finalize this in a sentence, we'd say that the initial amount invested was 105,477.02. Okay. And so that's it for that problem. Let's take a moment to learn about the letter E. So E is a special number that represents the irrational number, 1 plus 1 over n to the nth power, as n increases without bound. The letter E is used as a base for many real-world exponential models. To work with the base E, we use the approximation that E is about 2.718282. This was named after a Swiss mathematician, Leonhard Euler, who first investigated and discovered many of its properties. So calculate the following and round to 5 decimal places. So go ahead and take a moment and go ahead and calculate all of these and round them to 5 decimal places. All right, is this what you obtained for that? Hopefully it was. And if you don't have a calculator with you, so scientific calculator will do, but you can always use Desmos. You can use this on your phone calculator as well. But we're just going to use this button here. I'm just on the Desmos scientific calculator. So from the main, we're just going to hit function. We're going to hit E, and then we're going to go ahead and raise that. Notice that this is that approximation that we had. So we're going to go ahead and raise that. We're going to use this AB function. And we're going to raise it in that first case, come back to main and put in 3.14. So notice that's how I got that value, 23.0187. For this problem here, notice that what you're doing is you are plugging in 4 into this expression here. So you do have to simplify that first before you plug in 3 times e to that value. Okay. All right, so for now, let's go ahead and pause there. I'll do the continuous growth and decay formula in another video.